This is an overview and a walkthrough about the new system that I've built throughout this semester, which basically is an extension on what I did in the last semester. In the last semester, the idea was to build a base-free standalone tracking system by utilizing the SLAM technology implemented natively by MetaQuest VR headset like this one. And the full implementation basically was about taking the tracking capabilities from here and using inside-out tracking instead of outside-in tracking to stream the 6DoF data from something like this device into Unreal Engine, and then having a rig like this with a camera placed here, driving the both the virtual and the physical perspective in order to have a complete virtual production experience. Now, the current system basically built on the same idea, but the main objective here was to extend virtual production experience beyond just background-based compositing, meaning that virtual compositing and the merging between the physical and the virtual environments is not only limited to the background like in conventional virtual production systems. This system also offers compositing foreground and middle ground elements virtually on top of the physical feed, live action feed, by using AR objects. In order to do that, there was a necessity to use some sort of a depth sensor. And in this specific application, I ended up using the Z2i. The initial idea was basically to add the Z2i on the original rig that I just showed. But then I found out that actually the Z2i itself has an IMU, which was great because that meant that I can actually get the tracking from the Z2i. So by adding the Z2i into the physical rig like this, we have unified three main functionalities of this system into one sensor. We get the depth, we get the skeletal tracking, and we get the camera tracking, all in one piece of hardware. For the occlusion, the initial iteration was based on the skeletal tracking. Since the Z2i supports skeletal tracking out of the box, the idea was to just get the tracking driven by the skeleton of one or more performers present in the frame, and then there will be a holdout mesh that just shows the tracked skeletons, the tracked performers, on top or behind or above or whatever 3D objects within the scene. Of course, because of the physical offset between the two cameras, the perspective was lost and it wasn't rendering correctly. But the initial result showed a very basic level proof of concept. After that, there was the use of Churuku board, and I recorded the data simultaneously on both cameras and ran the spatial calibration pipeline in order to align the two cameras temporally and spatially. Once the spatial calibration was built and it rendered all the values needed to match the perspective between the two cameras, I basically took those values and put them into Unreal Engine's camera, and then ran the same the same skeleton-based occlusion process. This time there was a big difference because the performer was rendered within the skeleton correctly, and the movement and the tracking was much better. With that being said, this was still skeleton-based occlusion, so that was not true depth occlusion yet. In order to accomplish true per pixel depth occlusion, without the dependency on a skeleton or the existence of performance in the frame. The plan was to take the depth map directly from Z and route it into Unreal Engine. This happened by first a custom-made Python script that uses the Spout library to take the depth map and deliver it through the GPU into Unreal Engine and have that final output on a rendering texture. Then that rendered texture would be subjected to a 3D projection via an HLSL material that basically applies the same spatial alignment process from earlier to reproject the depth map from Z space into Sony's space. Once that is done and configured, there is a custom-made compositing material that combines the final reprojected depth map from Sony's space with the CG camera inside Unreal Engine that also matches Sony's space, and puts all of that together as the main compositing material in Composure. And Composure will deliver the final composited output via a rendering texture. That rendering texture is the final output. Basically, we have full compositing with depth occlusion. So we have the tracking working in the background on the LED wall, and then we have those foreground objects that are occluding the objects within the live action environment. So you can see the virtual background on the LED wall is tracked and synced with the movement. And I'm also getting the depth occlusion as expected. As for the skeletal tracking, this was still utilized and used for the interactive layer, driving the interactive AR objects based on the Laban movement analysis principles. That also delivers a different level of immersion and offers a different user experience.